higher dimensional objects. That's to see. So any quantum mechanical system or most of them have a huge number of the energy state, energy level. For example, the hydrogen atom, according to the Schrödinger wave equation, have the energy levels, which the first one is the ground state, the second one is the first excited state, E3, if you have some number of the particle and the particle want to occupy the energy levels, they want to occupy the energy levels. You have an n as the total number of the particle. And for each particle you have this story. I mean, for each particle there is a possibility for the energy levels. So you have n particle, and then n particle want to occupy the energy level, energy state. We should be careful about the type of the particle which we are using. Some of the particles can sit together in the one energy level. They are called bosons, and some of them follow the exclusion principle. So it's impossible to locate two more electrons in the one energy level. Anyway, when we need, we will specify that what's the type of the particle we will specify. So anyway, very, very roughly speaking, we can say that if you have an n particle, so some of the particles with non-reson or with reson, they are located at the first level. So finally, the first ground state will be occupied by the sum number of that, this is the sum number of the particle. And the same for the second level, and the same for the third level. The question is that how many different configurations exist to localize particles in energy state if we want to have total E. This is some fixed number. So I have some number of the particle and have some level of the energy. So I wanted to get exactly the energy, which I call it E. You know how to write this equation. So each energy level is occupied by some number of the particles. So basically the energy of the first ground state will be multiplied by the number of the particles seated here, and that will be the same. Also then multiplied by the, for example, 2 electrons will sit here, or 3 electrons here, or 4 electrons here. So the total number of energy will be 2 multiplied to E1 plus 3 multiplied to E2. In many quantum mechanical systems, you have these two equations. The one is the constraint of the number of the particles, so this is actually a fixed number. And the second is that you have also that, this is a fixed. And in most case, you wanted to find this Ni, because I don't know that how many particles will be sit that or here. So this is actually a density. So I wanted to find that the density of states. In each energy state, how many particles sit there? This I is running from 1 to n. But not all the systems have discrete energy level. There are some systems we have a continuous energy level. For example, the free particle in quantum mechanics has the spectrum of energy given by P squared over 2m, the free moving particle. Or if you want a more advanced example, I can give you a very advanced example. You have a magnetic field like that in the z direction. This is the z direction. And just allow a particle, a charged particle with charge q, to enter this region of the space. And by solving the Schrödinger equation, you can show that the energy level will be very complicated than a simple discontinuous or discrete energy, or very complicated than the very easily written continuous spectrum. If you release the electron and allow the electron or this charged particle with positive charge to move in the region that you have the magnetic field, so you needed to solve the Schrödinger equation. So actually, by the this is the time-independent Schrödinger equations, and here this A is called the vector potential. I will ask you to solve this equation, but not now. Maybe I will give you as a homework to you. Anyway, if you take this magnetic field and solve this Schrödinger equation, I can tell you that the energy level will be made by the two parameters actually. The one parameter will be the n, and is a discrete quantum number will start from the 0, 1, 2 like that. A part of the energy spectrum will be like simple harmonic oscillator in quantum mechanics, plus a part with a continuous parameter, we call it the alpha squared. Alpha is a continuous parameter. That's actually the momentum in the x and the y direction. Anyway, I write alpha. I don't want to be dealing with the different parameters here. So you see that the spectrum of energy will be not discrete. So you will have some discrete energy level like E0, E1, E2, E3. And at the same time, some part of the spectrum of energy will be function of a continuous parameter called alpha. And talking about I wanted to tell you that talking about the state with the energy EI, which we call it Ni, here will reduce to something different. You need to say that density of a state for us will be the number of the particle number per energy, for example, E, I, and for the range of the parameter alpha plus delta. Because one parameter in the spectrum of energy will be continuous parameter, and the other one is just indexed parameter, so will be the discrete energy levels. Finally, I want to tell you that instead of writing delta and I, you needed to be very careful and sometimes use also an integral if the spectrum of the energy is continuous. Yes. So you will have a, this is a for mixed spectrum of energy spectrum. I know that was a little bit more quantum mechanics, but just to explain that. Just I want to clarify for you that such example existed actually. The state with the continuous energy level, it really existed. Except the free particle, because free particle is a trivial example of the energy as the function of the continuous parameter. Because here this P, you know what I mean continuous. This P is changing from 0 to infinity, so there is no limit for that. If the particle is freely moving. That is very interesting example of the system with the mixed energy state. But most of the time, the energy state, most of the time, the density of the state is just function of the one continuous parameter. So, I mean, instead of the Ni, which is NaNi, I can replace that by NaE. And the sigma over Ni will be replaced by the NaE. But you need to include maybe one more parameter. Anyway, this is some kind of the measure. This is a number of the particle, the n, and you needed also the density of the state, that how much any energy state is dense. So exactly the density, what you understand from the density. Anyway, we should not do that, we should not enter that. Later we will talk about the system with the continuous energy level. So our first example will be just a simple case of a simple quantum mechanical particle in the box. This example can be used to realize the statistical mechanics for the non-interactive ideal gas. Last lecture I was explaining you that also a little bit about how the system reached the equilibrium. As you remember, reaching the equilibrium or tending to the equilibrium, toward the equilibrium state. You remember that bare example, the simple example I told you, if you have a lot of customer in the market, so the market will be very soon reach the equilibrium state. And that's the same if you are talking about the particles. As much as we have more accessible state, the system will reach equilibrium quickly. Omega E is number of the accessible state. Accessible state for system with total energy E. With total energy
Doctor,
yes.
here, what's the difference between density of state and probability density in quantum mechanics?
Probability.
Probability density.
Oh, that is a yes. The probability is that Px, for example, d x, psi x and t squared. That's about the probability of the finding one particle or electron at the small region of the space, at the very small qubit. So that's exactly about the finding the particle in the configuration space. I mean, finding in the definite in the some region of the space with finite size. You are looking for the place that approximation, the approximated location of the electron, for example. And you know that the electron cannot sit in the one point according to uncertainty principle. So we are talking about the range. So just in the small piece of the space with the volume delta cubic x, you have this probability of the finding the electron. But here, this is what we are calling Ni. Ni is the number of the particles sitting in the level, so that's a different. And one more thing, which is this Ne is the probability, Ge is the density of the state. This is a completely different from that. So this is the density of each energy state. How many particles are seated in these energies? And this is the weight of this energy, weight of each energy. You know, in the probability function in quantum mechanics, I know that the energy also is important to know that the shape of that, because the shape of the psi is related to the probability by some advanced techniques. You can relate this to together, actually. We will define the statistical quantum probability, and using that, you can get the quantity called partition functions. Using the partition functions, I can give you the G. So there is a relation between them, but not so very clear. You needed to have some more step between them. But the basic interpretation of these two are different. This is talking about the weight of each energy state, and this is talking about the approximated location of the particle at the given energy. This is about the space coordinates, and this is about the momentum coordinates, actually. So that is about the momentum space, if you want to say, and this has happened in the configuration space. I don't know you remember this fact, but from the wave function of the Schrödinger equation, you can make a Fourier transformation and pass to the momentum space. I think it's not very clear now, or I can't do the calculation now, but definitely it should be some relation between the density of the state and the weight of the state and the momentum representation of the wave function. I mean, the Fourier transformation of that is related to that, because energy is related to the momentum. But this is not very easy, I think. That's not very easy. To do that, you needed to write down the expression of for the Fourier transformation. Okay, we are talking we write just number of accessible states with the total energy. But this is not the only possibility. Actually, you can look for the number of the possible configuration of the system if the system have the total number of the particle n, and they have the total volume v and the v. So omega will be, generally speaking, omega will be the function of the district, E, n, and v. And why we needed that? Because we show that by the omega you can get entropy. One more thing, and that's very important, is that entropy is the extensive parameter. All these three parameters are extensive parameters, n, v. So I mean that if you change it, the n to alpha n, v to alpha v, e to alpha e, so the s should be changed also. I write like that. Will be alpha n multiplied to s. For any calculations, you needed to check that, is it possible